Okay, I think we are in live now. So just just wait a minute. Let's just make sure um, everything is fine. Seems like everything is fine. And yeah, and so we are basically working on this project. If you're watching my live regularly, you know that I'm just implementing this GPT-2 model in Rust. So I thought it was, I thought it, it, it will be easy, but it's not actually. It turns out that it's quite hard. I would say it's not very much hard, but it still gives you some amount of complexity to into. Okay, so the thing is, at the same time, it's fun. That's for sure. It's really fun. I'm not sure how to rank this project. Somebody will say this is a intermediate level project. Somebody will say, this is a very simple project. It depends on your expertise, right? If you are like a very experienced Rust, if you are a very experienced programmer in Rust, I would say you can fairly implement this in a day, in a single day, or even 6 or 7 hours, something like that. But if you are new to Rust or intermediate level, still you are learning Rust, it will take quite time. For our case, I'm also still learning Rust, but still, um, we are going. I think I'm not sure whether we are going fast or you know, but we are giving all okay, I mean, we are giving what we got. Okay, so that's it. So the thing is, I just explained these what are the things, in my previous live. Before previous live, I talked about a lot of things, like what are the things you need in order to implement GPT or any sort of LLMs. We just talked about embedding layers and positional embeddings, token embeddings, and what is tokenizer, these sort of things. And we haven't touched the tokenizer part yet, but we will come that in a future. um, so we have some sort of a skeleton, which is a GPT-2 model. it's still not complete yet, but it is almost complete, I would say. Kind of like a 70 percentage or something like that. Still it need to no still we need to implement the 30 percentage. And there is a lot of optimization, and these sort of these sort of things we need to take care. We haven't touched that part yet. So you know but now, I think maybe we can switch the gear to grad engine. So the one of the very important feature, one of the very important thing in deep learning, which is back propagation. You can think of it as like a heart of deep learning. So that's the without that you cannot learn any kind of any kind of model is just a skeleton. So that is the actual grad engine is the actual process of tuning the parameters for specific use cases or specific data set according to it. That's where the real learning happens. um, I would say it's much more complex than implementing the model architecture, because you need to basically keep track of lot of states and lot of operations, and what are the operations make those results and graphs, these sort of things. And in this live, um, I think we can focus on grad engine. Maybe you know uh, uh, I think once we build this, we can get a clear picture of how we can approach this problem. So our model is still not complete yet, right? But it's relatively easy once we completed this part. Okay. That's why I'm basically wanted to touch this part, so that we can get move really quickly and fast. Okay. So the thing is, you know if you are watching my live stream every day, you know that we have this tensor class. uh, it's sorry, it's not a class, it's a struct, custom struct. So here, this is the actual data tensor engine. You can call that, you can call like that. So this is the data type, um, which is going to be our weights and data sets and everything, every parameter. So the entire number of basically the entire model itself is going to be a tensor type. What I mean by that is every weights of the model going to be a tensor type. So tensor type going to be a vector, dynamic vector with the F32. Right now we are building this for F32. Can we can switch to F16, something like that. Still, now we are implementing this for F32. Okay, that's sad. And so this is going to be the weights and everything, right? So now some of the properties, some of the fields we need to introduce this model. Basically, what are the fields? So when it's come to gradient sort of things, you need to know the state and the operation and the result, right? It's basically goes like this. Let's say we call a field called grad or something like that. Okay. it's going to be a boolean. Okay, and another one is going to be grad, let's say punk, and it's going to be some sort of a, maybe some sort of an, so there how I put this, the reason I'm introducing these new fields is because you need to keep track of which are the tensors are need gradient, and which are the tensors don't need gradient, right? I earlier said that everything going to be a tensor type, right? This is a custom, this custom tensor type, but every sort of tensor don't need to be sort of like don't need to be involved in the gradients graph, right? Because weights, the model weights are going to be changed. We should involve in the grading graph, but the inputs not going to be changed at all. It's going to be fixed. So we don't need gradient for that, right? We don't need compute gradient for those, because we are not going to change them. Because the reason why we do this is because model need to learn from the data. It need to modify its parameters according to data, so that we can well fitted the data distribution, right? So the boolean is basically representing that this tensor need a gradient or not. Okay, the f function is basically, I'm not sure how to annotate this, because it actually need to, maybe we can set this something like a str type for now, but I'm not sure. Maybe we can change it in future. The another thing I need to mention here is that some of the things I'm implementing here is basically inspired from PyTorch implementation. The PyTorch framework, they have some sort of these some you know some sort of graphs and variables for keep tracking. It's much like that. Yeah. Yeah. So sorry for that. So that's how we are going to implement it. And so another thing we need to, so it's going to be required grad, I think. One of the bit hardest thing, it's about building complex project, is that the naming scheme. It's I'm not sure whether everybody find this hard, but I do find that hard, because it's it's for me it takes a lot of my mental energy to think to come up with the right name. And maybe we undergrad, so it's going to be something like so we it's going to be use, let's just for now let's just set it to f32. Okay, and this thing and this thing we don't need to set it to bug. Maybe just Okay, and another thing we need do some, let's say we are building default rate for tensor, and yeah, and the default. So going to be return the self, right? It's going to be return the self, and let's just return the self. Here, what are the things? So we need to make this as a kind of a dynamic thing. What I mean by that is some of the fields are going to be as initialized by the user, and some of them are default. So how we can handle this? Because in Struct, I think in Struct you cannot assign specific fields. You need to assign entire structure, right? Just wait a minute. Am I lagging? Why am I lagging? It seems like I'm lagging or something like that. Come on. Am I lagging? If I seems like kind of lagging, can you tell me please? Can you put it in the chat? Seems like I'm not now, but okay. Let's just get into this. Okay. So how we can do this? say some of the things need to be came from, you know, come from. Let's just ask GPT. I have a custom stack, and I have Punjab fields in it. And I want same some help. Oh my god, just wait a minute. Send some value to it defaultly, something like this. Let's just copy the code. Here you can see that I have lots of fields, but I need to assign this. I'm not sure how to call this, whether to assign or initialize. Whatever. Initialize the field. Send this field to send this. If I make any mistake, sorry for that. Add field to true by default, and sum of and data initialized, let's say initialized by the user. How can I do that in Rust? Okay, to achieve this in Rust, use custom trade. Okay, implement custom trade. That's what I'm trying to do. So this can be override by the user later. Is there any much better way to do it? So default tensor.mirror data this is the much better way, and how experience it's my live is lagging. It's kind of I can see here it's kind of lacking. I'm not sure why, but I can see here. Maybe we can restart our live. Oh man, that's fine. Yes, this is how exactly such a case. You know, Rust is a safe language, but it still complicates a lot of simple stuffs like this. I just copy this and okay. So it's all implemented by default. All initialized by default. When we want, we can do that. Okay. Okay, that's how it is. We don't have any other choice. Why am I lacking? Just check the memory. I still have plenty of RAM available. Okay, let's go on. Okay, so now the thing is, we just created, just assigned everything defaultly. So by default, it's going to be true. Require cat, it's going to be true, and it's going to be the gradient. I'm not sure. Yeah, it should be an vector, right? Because we are computing. Okay, now that we have this, we can start from here. So now we have some sort of fields for basically keep track of the steps, gradients, and operations. So those stuffs. Okay. So let's assume that we have some sort of a thing here, and so this is we don't need this. So what um at the end of at the end we are going to call the backward. Okay, once you find the loss, we are going to call the backward thing. So when we call the backward thing, it need to be it's basically like going backwards to the computation and calculating accumulating gradient and sort of like changing the parameter accordingly. Okay, so for now, okay, this is how you know this is how actually Okay, it keeps bothering me, something like that. So my stream is kind of like a laggy. I don't know why, but I'm not just restart. I cannot just restart the live again, right? Okay, leave it. So so the so now we need to ask the right question. Is that okay? I have a custom just okay. Now we have something like this. Then now we can store what are the things now we can know the vector, we can know the tensor is going to be basically tensor is need to have a gradient or not, and the another thing, what are the operation we are going to do with the tensor, and the another thing, the actual gradient, right? So gradient is basically in order to calculate the gradient of something, right? So it's a function. Let's say it's a function of a, and a is a parameter, a is some value, and we have some equation, and we are putting a into the function, and we calculated some answer. We get some answer, right? So the gradient is something like a is the input. It goes into the function. It produces some output, right? So if a change a bit, how much it's going to affect the output? That's the basic question of the gradient. Is if I change the a something like a very small number, I change it's up to you. You can change up to big. You can take big steps or small steps, but it depends on it. So if I slightly increase a, okay, let's say I have a, let's say a is 0, 0.5, let's increase to 0.6. How much it's going to affect the how much it's going to be affect the output of the function? um let's say when I input a as 0.5, I get a 2. If I input a as 0.6, I get the 3. So it's a 50 percentage increase, right? 50 percentage increase. Before we got 2, now we got 3. So the ratio is um, what crucial here. So that's what we are trying to do. When we when we are going backward, we the thing we need to have is we need to know the operation. At the same time, we need to have the actual vector. Is because is because you know if you let's say we are calculating the gradient for it. So in order to calculate the gradient, you need to have the input, right? Because that's only you can you need to have the weights. Actually, you need to have the weights. So the weights are the thing going to be changed, right? We are basically optimizing the parameter, right? So if we are optimizing the parameter, we need to have all the tensor in our model, weight tensor model, right? So that's basically meaning that it's when you are going forward, right? Let's say here is the data and here is the loss. So we are going this direction. So once you go this, you are getting into the GPT block, and we are getting into the block and MLP and LANOM, attention, etc., etc. Right? Once you end this, you need to keep all of those things in a memory. It's not going to be deleted. That's a very important thing here, because if it is deleted in the memory, then you cannot change the weight, because that's it. You cannot change the weight because you don't have the weights in the first place. So how you can change? So you need to keep that in the memory. Let's assume we haven't done that yet, but let's assume we have so we are keeping that in a memory. So once we calculate the loss, we need to come back. So once we calculate the loss, the first what we are going to do is come back and, hey, here the loss I have and how much you affects me. Okay, we are talking to the first layer of weights in the backwards, right, reversed manner. So maybe it's soft max layer or something like that. We need to talk about, hey, I am the loss. Okay, how much, basically how much you are affecting me. That's basically what uh, we want to ask, because the loss is computed by some amount of operation before the loss. Okay, before the loss, the step is, before the loss the model predicts the logits, some probabilities. Then the probabilities is converted to go through some steps. It's converted to loss. So the loss can ask the probabilities, hey, you are the input. So if you change something, if you change a little bit to something, I can change too. Okay, if I want to decrease myself, sort of like if loss need to decrease, how much you need to change. I want the ratio. I want to know the ratio. That's all it's asking. Over time, it will all reach the optimal place, so that the so that the you know so we will get the best parameter. Okay, so that's how propagation works. Okay, so we can track it in back for the next function. Okay, here what we have, matrix multiplication. So just call this as a so z is produced from here, and z f1 have the add block backward. So function is was created from the tensor with, that's fine. So we can trace back further. I'm not sure about how they implement back propagation. Let's just um, I want to know. mm, I want to understand deeply how the PyTorch implemented the back propagation. Back prop. So sorry for Google, Gemini or OpenAI. I haven't subscribed them yet, um, but they are still useful for me. The initial search result have provided solid foundation for understanding how a autograd engine, the core PyTorch automatic differentiation, dynamic computation graph, how PyTorch record operation and tensors, the backward function associated with each non-leaf tensor, which knows the backward function associated with each non-leaf tensor, which knows how to compute gradient for its gradient for its. I'm not paying attention here. The the backward function associated with each non-leaf tensor, which knows how to compute gradient for its input. So backward method, the triggers for initiating the back propagation from the scale loss. Okay, attributing where accumulating gradients are stored for leaf tensor, C++ backend. Attain the underlying library that provides the core tensor operations. However, to provide a deep explanation, I need to go beyond high-level overview. I want to elaborate interplay between Python frontend. Oh, there's okay. They implemented in the C++. Explain the data structure in more detail and trace the execution flow of backward more concretely. Okay, let's dive into this. That's what I want. The current search result hints at these deeper aspects, but don't fully flash them out in the consolidated manner. For instance, I know a turn exists, but I want to understand its specific role in automatic differentiation beyond just being a tensor library. I also want to detail the structure of the grade fn and how it's linked to graph. Therefore, the next step will focus on sympathizing the existing information and structuring it and the comprehensive narrative that goes the user Python code down to the underlying block. Okay, I want enough information to produce without further searches. I will now structure the answer to provide the deep dive. Okay, the final answer plan. Start with the intuitive analogy to frame the process. Okay, Explain the Python front end and back end. Okay, am I reading the thoughts of this model? No. But it's much more feel like I'm reading some sort of thought. The two layer architecture explain the okay. The forward pass in detail explain the creation of tensor objects and the require grad flag. Okay, details how each operation creates a new tensor with the grad fn. Okay, describe the grad fn object and how it forms the node of the dynamic computation graph. This is the main thing we need to focus. Okay, let's go through. Okay, the backward call explains what happens when a dot backward is called on a scalar tensor. Describe the role of autograd engine in traversing the graph. Explain the chain rule in the context of GN execution. Okay, then the C++ backend's role. Explain that Ayrton provides the actual implementation of forward and backward operation. Ayrton provides the actual implementation of the forward and backward, and oh my god. Clarify how grad f1 is Python. Clarify how the grad f1 is a Python corresponding to a specific backward function gradient accumulation. Explain how gradient are accumulated in the grad attribute of a leaf tensor. Mention the importance of the optima.0 grad. Putting it all together with the code explain example and a visual representation of a graph and backward flow. Okay, it's kind of planning now. This model is kind of planning. And upon tensor.autograd hooks and compiled to show the depth of system, this is structured approach will provide a comprehensive and deep understanding of. Okay, let's get into this. Okay, where we left off here. So the core philosophy dynamic tape recorder. Okay, imagine a tape recorder that doesn't just record the sound but record mathematical operation. Okay, the forward pass as you play your music, specific calculation on tensor, the recorder diligently notes every single operation you perform in order to do that. Okay, what it's saying as you play your music, perform calculation on the tensor, it records and note every single operation you perform in order to do that. This record is a computational graph. That's how, okay, I can understand this. Backward pass. When you want to revent, calculate gradient, you play the tape backwards. That's also already we know that. At each step, the recorder know the undo for the operation. Mathematically, this undo is a derivative. That's also we know that. So how they building the graph? That's we okay, all the thing we are searching as how they building the graph. Okay, AutoGrad is a tape recorder. Yeah, few feature is a key feature is that this graph is dynamic. Okay, so it builds from scratch every time you do the forward pass. Of course, it have to. This is why you can use standard Python control flow like if or for loop in your model, offering incredible flexibility compared to the static graph of older frameworks like TensorFlow. Okay, the two-layer architecture, Python and okay. C++ backend. Python magic lies in the dual language design. This is what still now the model is saying that we are going to cover this, we are going to cover this, but when let's just dive into this. I want to know. Okay, Python framework. This is what the users interacts with. It designed for easy of use, flexibility, and expressiveness. When you write C equal to A plus B, you are using the Python API. We are using what? We are using the Python API. We are using the Python API. Okay, and C++ backend. This is where the heavy lifting happens. For performance, the core tensor operation like matrix multiplication and convolutions and the autograd engine itself are written in highly optimized C++. Of course, that makes sense. Is A10 is a fundamental C++ tensor, a tensor library. Okay, a10 so it's in short it's a10, right? So the tensor library that provides the hundreds of mathematical operation of tensors. Okay, we have somewhere around two or three something like that. So let's trace the journey of single computation to see how these pieces fit together. Python tensor object is essentially a wrapper around the C++ tensor object. Okay, so the forward pass. Building the graph. It all starts with touch tensor object and the crucial it's all start with the tensor touch tensor object and the crucial flag. Okay, so creating a node, you are creating a input tensor and your model parameter, weight and biases. These are the leaf node of your graph. By setting true on your parameter, you tell PyTorch, I want to compute with this respect to this tensor. I want to compute gradient with respect to this tensor. Maybe what I can do is maybe I can I have some idea. Once we read this fully, we can get into this. Tracking operation, creating grad fn. Okay, when you perform operation on a tensor where at least one has a record grad true and the new tensor is created. This new tensor has a special attribute called grad fn. When you perform an operation on a tensor where at least one has a grad true and a new tensor is created. Okay, new tensor is created. This new tensor has a special attribute called grad fn. Okay, so the result tensor C now know how it was created. Its grad fn attribute point to the object in the case. Okay, this object is a node in our computational graph and it holds all the information needed for the backward pass. It holds all the information needed for the backward pass. Maybe we can do something like this. Okay, it knows the operation that was performed multiplication. It holds the reference to the input and A and B. Crucially, it contains the formula for the derivative of that operation. Okay, what are the things it knows the operation that was performed multiplication. It holds the reference to the input A and B. Okay, it holds, okay, that's the thing I'm planning to. That's the thing I can plan, just thought about that. We can just assign each of the reference to a tensor, which are basically computed. Okay, what I mean by that is, if I have a C, then C need to have the address of both A and B. And crucially, it contains the formula for the derivative of that operation. Derivative of the operation. Okay. Chaining the graph. This process continues, building the directed acyclic graph where each grad f1 points to the grad and reference of each input. Where each grad f1 points to the grad f1 of its input. What do you mean by that? We have a D and we are adding E, so add backward, and if you were inspected, you would find that it points to C. You would find that it points to C's grad fn and D. Okay, that's it makes sense. So E grad fn is okay, add backward, and if you were inspected, you would find that it points to C's grad f1 and backward. So C's grad f1 have this, and D is a new thing. So the code step are grad ID A leaf through mal B through mal. Okay. Maybe we can implement this much more simple way. Okay, once you finish this, we'll get into that. Okay, let's just go through this quickly. The backward pass, traversing the graph and the applying chain rule. This is where the magic happens. You typically have a scalar loss value at the end of your forward pass. When you call backward on the scalar, the autograd engine kicks into the gear. Okay, initially the flow. The backward call starts the process with the initial gradient of 1. What? The backward function start starts the process with the initial gradient of 0.1. Since did how do I pronounce this? This is starting gradient flow. Okay. The 1 is basically for, it shouldn't cancel out with the 0. Why am I? Okay, for now let's just pass. Calling the root, the autograd engine looks at e dot grad f1, add backward. Okay, the autograd engine looks at the e dot grad of an auto back. It passes the it passes the incoming gradient initially 1 to backward function of the object. So it passes the initial it process the incoming gradient initially 1 to the backward function of this object. Applying the chain rule, the backward function of the addition operation know that gradient will be respected to both of its input is just the incoming gradient. So it passes the gradient of 1 to both C and D. So they are adding them. So the gradient for E, actually the gradient for, actually the gradient, um gradient for C and D is 1. Am I right? Gradient of the E, I mean basically the ratio of changing, how it's changing is basically constant. I mean it's not a constant, it's a 1. Okay. For D, it's a leaf node. For D, it's a leaf node. The incoming gradient 1.0 is accumulated in D dot grad. Okay, now the gradient, okay, the one gradient is accumulated in D dot grad and both the Z dot grad. For C, it's an intermediate node. Yeah, C still need to go long way because D is created in the halfway. So but C have a balance. So the engine takes incoming gradient 1 and calls the C grad F. Interesting. So now C have 1 accumulated, the it's also intermediate. The engine takes the, okay, that makes sense. Continue through the traversing. The backward function of the now executed mal backward x 0 now executes. It knows the formula for the derivative of the multiplication. C is equal to A times B times B. The gradient with respect to A is B, of course, and the is B times text incoming gradient times the text incoming gradient. So 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 the previous gradient is multiple now. Already C have a gradient of 1, right? So now we are basically finding the gradient for A and B. Okay, so the A, for the gradient of A with respect to A is B, is because they are multiplication, and when you find a derivative of that, A will be cancelled and B is the constant. So B is the thing you have, and for B it's A, and you need to multiply the previous gradient to both of these variables. Okay, so that it's going to be B multiplied A for A. Let's say here we have a B is 3 and A is equal to B for A into multiply 1 equal to, okay, do you understand what I mean? So the reaching the leaves, these calculated gradients are then passed to, I hope this line makes sense. It's basically just, for A it's a B into 1, for B it's a into 1. So like here A is 2 and B is 3. Okay, reaching the leaves, the calculated gradient are then passed to A and B. Okay, calculated gradients are then passed to A and the B. Okay, now since they are leaf nodes, these gradients are accumulated in their respective dot grad. Okay, now it makes sense, right? So Step third, gradient accumulation and zero grad. So the gradient accumulation and the zero grad. So the gradient, okay, a crucial detail is that PyTorch accumulates gradient and the grad attribute. If you were to call e backward again without clearing, this is one of very important thing you need to keep in mind when it's when you're dealing or creating or some sort of writing your own grad engine. It's one of the very important thing is that nowadays you have PyTorch, you don't need to worry about, but this is very important. Just you need to set, once the graph is finished, you need to set the grad to zero grad, which is basically zero the every gradient to the next process. Otherwise it's going to be accumulated for the second training loop, third training loop. It's going to be accumulated forever. Okay, so if you're called to backward again here, because once we call the e backward, then the next time we are going to call the e backward is going to be after the second loop, right? We change the parameter, again we get into the single forward. Once we finish the single forward, then we calculate the loss, then only we are going to call this e backward. So without clearing the gradient, the new gradient would be added to the existing one. That's one of the major thing you need to keep in mind. Okay, this is why in every training loop you must call zero grad before the loss backward call. So this results the gradient attribute of all model parameter to ensure that they only using the gradient for the current batch. Okay, current batch. So the C++ connection in detail. So let's refine our understanding of gradient FN. The mult backward zero object in a Python is essentially handled to a C++ object. This C++ object inherits from a base node class. Okay, base node class. Okay, then sorry, when e dot backward is called, the Python code makes call into the C autograd engine. This is the this engine takes the root node and add the initial gradient, and it then calls the apply method on the C++ node. Okay, this apply method for add backward will. Okay, receiving the incoming gradient, calculating the output. Okay, receiving the incoming gradient, calculating the output gradient, which is just the same as the input gradient for the addition. Finding the next function. So okay, finding the next function in the graph in our case. Okay, querying up queue up or queue up a call to the apply method for the backward C++ object with corresponding incoming gradient. Okay, this process continue into the all paths in the graph has reached the leaf. The actual derivative formula, the apply method for each operations are defined in the C++ performance, and the register will be dispatcher. So the current one is called for define as a device the tensor on. I'm not paying attention. The process continue until to the all path in the sorry for that. The process continue to the all path in the graph and hatchery. The actual derivative formula applies method for for each operation are defined in the C++ backend. For the performance are registered with the dispatcher. So the current one is called for the device CPU and CUDA the tensor on. In summary, PyTorch propagation is highly optimized two-stage process and flexible and intuitive forward pass in Python that dynamically build a computational graph followed by a high performance backward pass executed by the C++ autograd engine that traverses this graph to compute gradients using the chain rule. Let's just implement it for now. So what they're saying is that, so let's just live with this. So now what we have this, now we have our tensor, right? So this is our tensor class, okay? And we have a method for addition, right? So what we are going to do is, now we have a grade, recurve grad in the function. So this should be um, it should be it should be something like an array with the address of tensor. Okay, this is what it should be, and we don't need this. Okay, so yeah. Okay, let's just restart our live. I think it's kind of a bit lag.